Hello, this video is on sinusoidal graphs. First of all, what is a sinusoidal graph? A sinusoidal graph is a graph produced by a trig function that looks like this and goes on forever. Simplest example of a sinusoidal graph is this function, or sometimes written as y equals sine theta. The only difference is when you see the x, then that value is in radians, and when you see theta, it's an angle, so it'll be in degrees. And you'll probably see me use both during this video. So let's get the general graph. Let's get the specific graph of y equals sine x. I'm not going to plot every single point of y equals sine x. I'll just get some of the key ones and then fill in the rest. So if I make a simple table here using 0, 90 degrees, 180 degrees, 270, and 360 for x, I'll get the y values of 0, 1, 0, negative 1, 0. So that would be here at 90 degrees, here 180, here 270, down here if that's negative 1, and 360 back to 0. And it's not going to be a jagged graph when I connect the dots. If you plotted all the x values or y values between the x values of 0 and 90, you would get a curve like this. And then between 90 and 180 like this. So it'll be smooth. And this part would be a reflection of this under the x-axis. And of course that would repeat, since sine is a cyclical function. So that would go on forever in both directions. So this is your basic sinusoidal graph. And sinusoidals have parts. So there is an upper bound that the graph does not exceed. There's a lower bound as well. And then since it's symmetrical about the x-axis in this case is also known as the sinusoidal axis. It's not always going to be the x-axis, of course, because I'm going to show you how we can move the graph up, down, left, right, and change other things. The distance between the sinusoidal axis and the upper bound, or the lower bound, this distance right here, vertical distance, that's called the amplitude. So that means this is also the amplitude. And since this graph repeats, there is a cycle that repeats over and over again. For example, if I treat this as sort of the, quote, starting point, then I get all my values and then I come back to the starting point where it starts all over again. And that takes 360 degrees to happen, from 0 to 360 degrees. So since one cycle lasts 360 degrees in x, then that is the length of a period in this function. Now in different functions, I can alter things to make the period shrink or extend. For y equals sine x, the period is 360 degrees, or 2 pi. Do I have to treat this as the starting point, the quote starting point? No, because if I started here, then the cycle would go from here to here. That's beginning to end. This is where the curve would start all over again. And since that would happen at 450 degrees, from 90 to 450, that's still 360. So whatever point you start at in a sinusoidal, the period will always be the same. Okay, so that's y equals sine x, or y equals sine theta. How about y equals cosine x? Okay, I'll spare you the chart this time. That should be 270 and then 360. So I marked 1 and -1 because the upper bound for cosine is 1 and the lower bound is -1, just like sine. And the cycle for cosine is also 360, but when x is 0, cosine is actually 1, not 0, like in the case of sine. And then when at 90 degrees, cosine is 0. At 180, it's -1. At 270, it's 0 again. And then at 360, we're back at 1. And it looks like a V, but it's going to be smooth just like sine is. So like that. And then of course it'll continue in both directions. But you can see that the cycle lasts 360. You can see the sinusoidal axis is still the x-axis. The upper bound is 1, the lower bound is -1. That makes the amplitude 1. And I already mentioned the period's 360, so that's all the parts we have. Okay, so commit sine of x and cosine of x to memory, because we're going to start altering the basic general equation y equals sine x and y equals cosine x, adding coefficients and adding and subtracting things, and changing the value of x, or the argument, x or theta, to see how the graph changes. Okay, to understand how it changes, first consider that y equals sine x can also be written as y equals 0 plus 1 sine x minus 0. Okay, that's the same thing. But if I change any of these values, then the graph is definitely going to change. Also, with cosine, I can also write that as this. And likewise, if I change any of these values, the graph of the sinusoidal will change in the same manner. So what do these values do? Well, here's the general form. I could also use theta minus d. Okay, we'll see. Let's start with A. That's the amplitude. So back in our sinusoidal, our sine y equals sine x, the amplitude, as I pointed out earlier, is 1 in that case. And 1 is also the coefficient here. So when A is 1, you get an amplitude of 1. Right here, C, we call that the vertical shift. And this should be familiar to you, because if you take any function and you add some value to it, then the whole function moves up or down, based on whether C is positive or negative. So that's something that's true for all functions, including trig functions. B has to do with the period. We mentioned the period being the length of x that spans one cycle. And I mentioned that you could expand the period or shrink the period. So to determine the period of the sinusoidal, you take 360 degrees, or 2 pi, and you divide by b. Okay, so this value is a little different than a and c, because a and c are values that directly reflect something in the graph, whereas b, you have to take 360 or 2 pi, divide by b, and then you know the period. So you have to do a little calculation. And then d, this is called the phase displacement. That's just a fancy word of how much the graph shifts left or right. Okay, this should look familiar because in any function that we've done this year, if you have in parentheses the independent variable and you subtract something, that means it shifts to the right. And if you add something, that means it shifts to the left, right? Okay, so we're going to do an example here. Y equals 3 plus 4 cosine 5 of theta minus 10 degrees. So, draw my axes. Okay, the first thing I usually do when I graph sinusoidals is I get the upper bound and lower bound. Well, I get the where the sinusoidal axis is going to be, I locate that, then I get the upper bound and lower bound. So, since the vertical shift is 3, that means that your normal parent cosine function, is going to shift up 3 from where it normally is. What is your parent function? The parent function is what we did here. This is your normal cosine parent function. The sinusoidal axis is normally the x-axis. So, if I have a vertical shift of 3, that means my sinusoidal axis will be at 3. So I'll make this 3. There's my sinusoidal axis. Now my upper bound I will locate by identifying the amplitude and just going up 4 from this sinusoidal axis. So my upper bound is going to be 7, and my lower bound will be at -1. Okay, so now I got my framework. I know that I can't go higher than this dotted line, I can't go lower than this dotted line. Okay, now I'm not going to impulsively start my first cycle here, because the cosine graph will only start at the y-axis if there's no left-right shift, no phase displacement. But if you look here, we do have a phase displacement, so it's not going to start here. It's going to start at 10 degrees. There. So at 10 degrees, my y value is 7. And I'm not going to draw it yet, but if I trace the first cycle, it'll go like this, hit the lower bound, and then come back up and finish one cycle, we'll say here. Now what I need to know is how far is that? How long does it take to finish that first cycle? That's the period, right? So I need to look here. 5. Remember, this is the one where I have to do some calculation to get the actual period. It's right here. 360 divided by 5 gives me 72 degrees. So that means this first cycle, which I will now draw, takes 72 degrees to happen. So that means 10 add 72, I'm now at 82 degrees. And then the halfway point here would be, well, that would be 36 degrees long, so that would be 46. And then now I've got one cycle, I can draw another cycle. And I know the period is 72, so I just add another 72 to this. That's 154. And 2 cycles are enough. You probably need to draw 2 cycles to make sure that whoever's reading your work, knows that you know how long the period is. Okay, let's do one with sine now. And this one's going to be in radians as well. Okay, so I get the vertical shift to find where my sinusoidal axis is going to be. It's -5, so I'm going to go 1, 2, 3, 4, 5 down. That's my sinusoidal axis. The amplitude is 4, so up 4 for the upper bound, and down 4 for the lower bound. Okay, now there's a phase displacement here, so the sine curve is going to start pi over 2 to the left. Pi over 2 to the left. That's 90 degrees to the left. So I'll make this negative pi over 2. And that's where my sine curve is going to start. And remember, sine curves, going back to the parent here, they start, quote, start because there's really no start. They start in the middle. They start at the sinusoidal axis. They don't start at the upper bound like cosine does. So there will be a point at negative pi over 2, negative 5 here, right in the middle. Okay, and then now I need the period. So I grab the 1/3, and since I'm in radians, I'm going to do 2 pi instead of 360. Okay, so my period is 6 pi. So if I add 6 pi to negative pi over 2, that's 12 pi over 2 minus pi over 2. So that's 11 pi over 2. So 11 pi over 2, I'll put that here. That's where my cycle is going to end. So now I can draw it. Sine curves always start going up, positive slope. Okay, there's my first cycle. And halfway point is right here. And that would be 3 pi, right? Half of 6 pi is 3 pi. So 3 pi from here to here would put us at 5 pi over 2. And then you can draw your second cycle by adding another 6 pi to 11 pi over 2 to get the next one. Alright, now that you know how to graph, and you understand the connection between the equation and the graph, we should be able to get the equation from a given graph. Okay, so so what you're given is a sinusoidal at negative 30, lower bound negative 40, okay, this is probably going to be a terrible drawing because I didn't mark this very well. Okay. Okay, so that's all we're given. Just like when we're graphing, I'm going to start with the sinusoidal axis. So the sinusoidal axis is given here at negative 30. So starts off negative 30. And then since the lower bound is at negative 40, that's an amplitude of 10. Okay, now here we have a choice. Every sinusoidal graph can be expressed as a cosine function or a sine function. And you have enough information given here that you could express it as either. So if you wanted to express it as a sine function, you would use this as your quote starting point, and this as the end of your first cycle. If you wanted to express it as a cosine function, you would use this as your quote starting point. This would be your halfway point, and then whatever x value this peaks at, that would be the end of your first cycle. Okay, I'll do both just so you can see how to do either way. So if I express it as a sine function, this is my starting point, which means my parent has been shifted 2 degrees to the left. So I need theta plus 2 degrees there. If you want to express it as a cosine function, I have not moved the graph at all, so the vertical shift is the same, the amplitude is the same. I'm using cosine this time. And now my starting point is in a different place because this is my cosine function starts at the upper bound. So this is the parent moved 3 degrees to the right. So theta minus 3 degrees. Oh, I'm missing something, the period. So the period is, I'm looking at the sine curve now, -2 to 18. So that's a period of 20. And so the value that goes here has to be whatever that would be. So that would be 18. So 18 here, 18 here. Okay, so that's sinusoidal graphs.